area about sequential some stochastic optimization for some big data problem. So let me see. Oh, this one doesn't work. Okay, I'll use that. Oh, okay. So outline. So I will first talk a little bit about the background about the optimization and why we want to do the stochastic optimization. Then I will talk about some recent progress we made in this sequential stochastic optimization. So I'll talk two methods. So we studied and explain why it's better than the batch optimization methods. Then I will talk a little bit about strategies for distributed computing. One is with Shai about MiniBatch SDCA, the stochastic optimization method we worked on. The other one is a little bit different scheme. So there could be potentially a few different schemes for discrete computing. So I will describe something happens to related to the two methods. One is SDCA, the other is SVRG. So, okay, the background. So background is in machine learning. So we are interested in kind of optimization problem, but it has a special structure. The special structure mainly we are interested in looking at is sum over data. So essentially, so we want to do an optimization, and the optimization problem has sum over data. Each fi will be a simpler structure. And then we are interested in the sum over some simple functions. Examples like logistic regression, ridge regression, least squares regression, all have this form. So this is generally for supervised learning. If we have a large data, then we also think about doing distributed computing for that. But for now, let's just look at this particular problem and try to see how do we take advantage of the special structure. So if we want to look at this optimization, we can have simple to complex forms. The simplest form is a single machine, single core, which is what we will look at first. In particular, in our setting, what we want to say is in this scenario, we can use some kind of sequential algorithm, like SGD and so on, or our stochastic modifications of SGD. This can be implemented efficiently on a single core, single machine. If we move to the multi-core, then we have some other scenarios. But generally, multi-core is a shared memory machine. So you have a relatively cheap communication. So you can do something which you cannot do, for example, if you have multiple machines. So multiple machines, you have a more expensive communication, especially you want to synchronize the communication. And this way, actually, we will talk about later on. So one is we were starting from simple, but then we will look at this synchronized communication. Then you can have, if your communication is really a barrier, you really have to think about asynchronous updates, which hopefully can reduce your communication, but we will not talk about this scenario in this talk. This will be really to make scale large. Generally, what I will talk about is from simple to complex. So first, the simple one means we can do sequential algorithm. One more complex, we will think about how to reduce communication. First, we will look at this problem, just what I wrote down earlier. This is an optimization problem with a special structure. And if we know anything about optimization, where you take a calculus class, you know the standard method, or the first one you would heard about is gradient descent, which basically has this kind of update rules. One thing I want to compare with is compare with other approach is to say how fast this method can converge to the optimal solution. Generally, you have this kind of results. You compare local minimum, whether it's convex or not, doesn't matter. But the convergence rate depends on conditions. So for the case of illustration, we are more interested in strongly convex and smooth functions. So for this kind of problem, we know the convergence rate is linear. So those are classical results. Basically, the convergence rate after k iterations, it will be something smaller than 1 to the k. So that's generally referred to as linear convergence. in the optimization literature. Can be considered reasonably fast as long as your condition number is not too large. This is inverse condition number is not too small. Or as long as the rho is a constant, then your convergence fast. Compared to this, so there's a disadvantage about doing the gradient. So what the disadvantage is, if I starting with a special form like this, if I calculate the gradient, it takes n summations. So each time you have a gradient descent, you would calculate the gradient, which require n summations, which is very costly if your n is large for the big data problem. Now, one fix to that is to say we don't have to compute the exact gradient, especially in the beginning. We probably want to compute some simpler, say, approximation to the gradient, and a very natural approximation of the gradient is just using subsamples. So here is just the stochastic optimization. What we refer is mainly to say that the gradient is subsampled when you do the computation. We do a random subsample of this guy, and then instead of using the true gradient, we use approximation. And typically, when we do stochastic gradients, and we just size of B with 1, but we can use a MiniBatch, we can have a size of B is larger than 1. But this is general idea. The idea is we want to use approximation of the gradient. If we look at this approximation, so there are two things. One is this is unbiased estimator. If you're starting to look at just to look at approximation. The other thing is there has to be an error because it's not the exact solution, but it's approximation. The error, because it's unbiased, is variance. So when we talk about how accurate is this guy, close to that, we already talk about the variance. How large is the variance? And when you reduce sample size from n to b sample size, then essentially what you do is you are using a more efficient computation, but introduce the variance. And how large that variance turns out to be important as far as the convergences goes. So this will play a central role when we talk about the methods. Now let's compare with SGD and GD. SGD, of course, has a faster computation per step because you don't use a full sample, you use a smaller sample. You get a slower rate. This 1/t rate is because of variance. So you introduce a variance of the gradient, and the approximation, that variance basically is 1/t, so you cannot get rid of that. For gradient descent, we know that it's a worse computation per step, but it has no variance. Therefore, you have a geometric rate of convergence for the same kind of problem, strongly convex and smooth. Overall, so this says SGD is fast in the beginning because the slower convergence, because of the faster computation, and you do not need a very accurate gradient at the beginning. In the end, eventually, once goes on and on, you will need a more accurate gradient because you want accuracy. Therefore, the variance turns out to kill the SGD. So essentially, SGD fast in the beginning, but very slow asymptotically. This is linear. This is nonlinear. This is sublinear. So you draw this line. If you just compare standard SGD versus gradient descent, what you get is this curve. Basically, gradient descent, it goes slower in the beginning because of the computational cost. But then eventually it's getting faster because you have a linear rate, faster convergence rate. Here, SGD, you have a faster beginning because you don't need accurate gradient in the beginning, and you have a faster calculation per step. But in the end, when you really need a more accurate gradient, it doesn't provide that. You have a variance, then it's become slower. So a typical strategy, people actually do that in practice. I know several people who start doing that. Because of that, so we can use the SGD first to do the training. And at some point, let's say at this point, if you look at the marginal rate of convergence, gradient already become faster. Then what happens? You switch to the gradient descent or some other fancier methods like LBFGS. But essentially, they fall in the same category. They compute the full gradient. They don't use approximation. they are essentially what we call batch methods, not stochastic methods. So generally, that's the scheme. This thinking, I mean, makes a lot of sense until recently. Until I think 1 or 2 years ago, people realized that, in fact, this is not necessary. I mean, just from a single core, single machine optimization point of view, this is not the best approach. We can do better. And the better is through stochastic algorithm, but better, of course, because we have a variance in the stochastic algorithm, we want to fix the variance problem. So that's what I'm going to talk about. So I will talk about, if we summarize, SGD converge fast, computation is slow. That's a gradient descent. GD, that's GD, SGD convergence, convergence slow, but computation is fast. And the key I want to again say is that that's because you are not estimating your gradient accurately. You have a variance. And what you should do is, if you want to fix SGD problem, you think about fixed variance problem. So that's what actually made very recent a few papers about that. So about improve SGD, the central idea. Some of the papers, like the Francis Bach, this French paper, has very, very long proofs. You don't understand what's going on. So I don't understand. Nobody understands except the authors. But the point is, essentially, if you do stochastic optimization, if you have a fast convergence, it has to be reduced variance, period. There's no other way around, as far as I understand. And this makes it more clear. So I will talk about this first, just show you why this can work with the variance reduction. And here is another work with Zhang about using a kind of traditional algorithm in some sense. This algorithm has been known for a while, for at least 10 years. But the importance here, at least in our work, is analysis, but also stochastic. It actually turns out to be important to be stochastic, not deterministic. So when we do this kind of SGD or whatever improvement, SDCA or whatever, they need to be stochastic. They need to be randomized. And nowadays, a lot of people also in the optimization community interested in randomized coordinate descent, randomized whatever, basically. So here is a view about gradient descent from the variance reduction. So this one hopefully explains. If there's one slide you take home, maybe that's what it is. So if I have an objective function, have this special structure. So what I do is I start with some W tilde, which is close to the optimal solution. For example, after you do one round of SGD, you can get something close. Not exactly equals your optimal, but close enough. Then you do a compensation. The compensation is looking at the following. So you take this gradient, you subtract your own gradient at any particular point, and plus your full gradient. This one sum up to be 0 because this full gradient is simply sum of your average of your individual gradient. So essentially, this term sum up to be 0. Therefore, this function is equivalent to this sum. Basically, you do. Now you want to rewrite it in a different form. So why you want to rewrite it in a different form? What happens is I can do stochastic gradient with this function instead of this function. It is applied the same, except if I do stochastic gradient with this function, the variance is reduced. So that's the key point. Here, if I look at this, it's equivalent by using this compensation. But then my SVRG rule is actually looking at the stochastic gradient with this representation. So this representation, I will just do this SGD. And if you expand out in the original function, it becomes theta gradient minus this guy, which is basically this term plus this term. So essentially, you just have to do a compensation. The point is the original SGD has a large variance. It's a fixed variance, constant variance. There's no way you avoid it. But this guy has small variance. Why is that? It's actually not difficult to see. Here is why that has small variance. Variance actually goes to 0. Essentially, because once you have the your tilde is close to W star. After a while, you go a while, you find W tilde, you expand at that point. This is close to your derivative. So this guy close to 0. This guy close to that, simply because this will be close to W star. This guy should be close to W star. Therefore, this should be simple, close. And this one should be subtract each other. It should be close to 0. This guy should be close to 0 as well. Therefore, they're adding together close to 0. So the bottom line is once you do that, eventually what you can show is that the convergence of this algorithm become linear. The linear convergence has a particular form. And each iteration of this algorithm look at only one example. Therefore, computation is fast. It's computation fast and has a linear convergence. So that's the key point. And in fact, if you compare this convergence to the gradient descent, you see a faster convergence. The faster convergence is following, roughly speaking, just in a very loose way. So we have a condition number times this is generally gradient descent, but each gradient descent require looking at n examples. So total computation cost to have this condition number times n will be what you get. And if you look at the other example, what you have is instead of n times condition number of this one, you have n plus. So it's really n times goes to n plus, which gets you a lot of benefits, because when n is large, which is typically what the big data problem is, you really have a large n, and you don't want to have this one, you really want to have this. So this one essentially say, if n is large enough, you just go to a few rounds of n, then it's sufficient. It's always well conditioned. Basically, that's, and the condition number is defined as this. Basically, the gain of this kind of stochastic algorithm, when you correct the variance problem, is substantial when n is large. So that's the point. There's another algorithm okay, here actually is just an example of this is a variance. Variance of SGD is actually flat. It doesn't get reduced because you don't have any compensation. If you do this SVRG, eventually you get reduced. You keep updating your W tilde, the W tilde and your updates goes to reduce. So that the point is it can get reduced. You can do convex, non-convex, small non-convex problems. And then you have you see the variance gets smaller. And if you do the convergence, it's smoother because of that. So this is just some illustration. So there's another method, which actually turns out also very interesting method. It's a little bit more classical method about dual. You want to do dual coordinate. So you start with a primal problem. You look at the dual problem, and you look at the dual objective function, which I don't write here, but essentially dual problem is your primal rate is the sum of dual. And the dual basically is the derivative of your functions. Essentially what it says that you want to optimize dual. You look at the optimization in terms of the alpha, and you update the alpha. Eventually, this gets you an algorithm which people use, for example, solving SVM and so on. So this is algorithm. And recently, like Xia and I analyzed this one particular, getting similar results to say this one actually turns out has a fast convergence behavior as well. And the reason of that, again, you can look at this as a stochastic algorithm, and the reason of that will be the reducing variance. So if we look at the original SGD, so let's start with the original SGD. This will be what people do with SGD. Basically, each you have your loss function, you have a regularizer. So each time you take derivative, that's what it gives you. That's the SGD function. Now you can look at how it's updated in the dual. But essentially, the alternative of SGD is this SDCA. It's very similar form. You have the derivative of loss function, but instead of a derivative of W, you replace that by n times alpha I. The reason you can do that is essentially I replace this guy because W is the sum of alpha j. It's an average of n times alpha I. Essentially, I will take the expectation, just take one of that components. Then I will get basically a stochastic approximation of W. So I will double stochastic in some sense. One is stochastic not only on this term, but stochastic in terms of W using the dual representation. So this one comes from this guy. I'll just pick I because I is random. So essentially, I'll get this. So if you take expectation, it's the same. It's, eventually, it's the same formula, but you get a dual update. Essentially, this one is in the primal form. You can write that in the dual form. Basically, dual form is only one of the parameter gets updated. The other keep on change. So this is essentially the dual coordinate ascent. You look at each one. Look at one particular dual. You update that, and you are doing that. So that's basically the idea about that. The main point again is that if I study that instead of in the dual domain, which typically people study when they look at the coordinate ascent or coordinate descent methods, they look at dual. But if I look at the primal dual, mostly we are interested in primal, and this is a stochastic algorithm. Again, if you think about the SGD, this one is one version of SGD in the sense of this is a stochastic approximation of your gradient. The expectation of this one is a gradient. So if you look at it this way, what happens is that this one has small variance also. Simply because if you look at this guy, then you look at the dual representation, at the optimal, it's the same equation. Basically, the point is this guy goes to 0, simply because of that dual representation. And that also means stochastic variance goes to 0. This one, once your stochastic variance goes to 0, you know it's you get fast convergence. So that's essentially the similar result you will get. And of course, when you prove those linear results, you need a stronger than this goes to 0. You want to say this goes to at the right rate. For SDCA, you want to bound the duality gap. Duality gap goes down in the right rate. For the SVRG, you just dual suboptimality. The variance should be upper bounded by dual suboptimality. Here, the variance should be bounded by duality gap. So that's the thing. This one basically mainly says idea about the recent idea. Once you have this new stochastic optimization techniques, you can get faster convergence than the standard batch learning algorithm. Then we will think about parallelization, simply because what we are doing stochastic optimization are sequential algorithms. Sequential algorithms, they are useful when you implement that on a single core. You can do that sequentially. If you do that multiple core, for example, or if you do that in multiple machines, they cannot be parallelized. And one approach, there are different approaches to that, but I will talk about two things which can lead to parallelization. One approach is MiniBatch. So in MiniBatch, instead of using one example, you're using maybe, say, 1,000 examples simultaneously as a MiniBatch. Depending on problem, it can be hundreds of thousands. And then you distribute across, let's say, 100 machines. Each one handles, for example, 100 or 1,000 examples. Then it can be parallelized. You will save communication. The computation about the MiniBatch can be more extensive, more costly than the communication cost. In that case, what you can do is just doing MiniBatch SDCA. MiniBatch SDCA is very similar to SDCA. Basically, our similar proof will carry over. So that's essentially without change. Except the problem is, if you do the MiniBatch simple implementation, it will slow down your convergence. It will not accelerate linearly as your processor goes. You want to accept, for example, if you have 100 processors, you really want to say computation 100 times faster. But it will not happen when you do the linear. It will be reduced again. The solution, what we do is, of course, a lot of people are familiar with acceleration, Nestoff's acceleration methods. The other alternative, I would say, if you don't use acceleration, you can use second-order information, try to play around with that. This is more tricky, but I think it's doable. It just is hard to prove anything. This one is much easier to prove things. So we look at this so that we can prove something. Here is one version. I don't want to explain that too much, but essentially this one is one version of accelerated MiniBatch, SDCA, which worked with Zhang about, and this is a NIPS paper. This one is better than vanilla SDC, because a vanilla SDC, it can slow down once you go from stochastic. MiniBatch size goes up, especially when MiniBatch, if MiniBatch size goes to n, up to n, then you know it's become batch algorithm. So it will have slow convergence. The question is how large it goes. You can still have a good convergence. Here is what happens. You have, this is batch algorithm, accelerated gradient. This is a MiniBatch stuff. And once MiniBatch goes up larger, this one essentially means MiniBatch is n size, right? It will have slow convergence. Once MiniBatch size gets larger and larger, convergence should become slower. Eventually, it hits this guy, becomes like batch learning. But the question is how large it can be. You can tolerate still have fast convergence. Turns out when you do the acceleration, you can tolerate a fairly large MiniBatch size. For example, so in this particular example, you have a small MiniBatch SDCA versus a larger one. You still have a reasonable size. It almost has no loss of your convergence speed. Basically means if you use more processors, you get linear speed up. So that's conclusion. While here you really pace if you do the batch algorithm, you pace in terms of convergence speed. So another update I want to say. So this is one way to achieve. Another way to achieve that is the following scenario. Let's say you have m processors. Each one have 1 over m. And you want to solve that independently for each processor and try to combine that. In that case, each processor you can do a sequential algorithm because you do not have to parallelize that. So you do a sequential algorithm for each processor and combine that. One simple combination strategy is the following. So I will split this data into m different machines. Each one have 1 over m number of examples. Then I will parallelize, separate that, compute W1 up to Wm. Eventually, I will take an average. This is one scheme people studied. It has some, under certain assumptions, you can have some theoretical result to say this is good, but in practice, usually this is not as competitive to you solving the whole problem. Now, let's say if we want to take on from this idea to say we can solve problems sequentially on each machine very fast. We know we have things like SDCA, which achieve that problem. Then we want to say if we want to synchronize over different machines, is there any way we can do better than this, or at least try to a few more steps getting strong, getting good performance. So here is one possible improvement. Simple strategy run independently. You can run sequential algorithms and computation efficient. And this disadvantage is practically inferior. Solution, you want to synchronize more. You just repeat this step. The question is, how do you want to repeat? Right. So once you get this one, and what you go from there. Here is where actually you want to look at this form. M processors, you want to say, how do I want to speed this up? And this is a screen. It's basically the same as SVRG. The proposal is basically the same as SVRG, except you do a parallel version. So in the original SVRG we showed is sequential. You look at this particular transformation of your function. You do that sequential. We know this when you do this transformation, variance gets reduced, which means all the functions become very similar. And then what happens is once you do that in the original version, so you do that sequentially. Here we do that in parallel. But in parallel, what we do is we try to minimize this function with a modified W. each time. So each time we just modify W, and we solve that independently. Basically, this one is an iterative algorithm. The main point of this one, again, you have a fast convergence. So I don't want to go over that, but essentially, the idea is if you do this algorithm, you have a fast convergence, very fast. For example, original scheme, you have one step. Here, I probably have only 2 steps. I only need 2, 3 steps. It's not like 100 steps, but 2 steps. So that's the main point about this approach. And this one, again, is using very similar. One is, if you look at we talk about 2 algorithms. One is SVRG, SDCA. SDCA, we talk about MiniBatch. SVRG, we can have a parallel version. So they are all connected to each other, the ideas. So in summary, so what we have is we have optimization in machine learning. People ask me, like Nina asked, what's machine learning brings to the optimization. So I would say one thing is a new problem, but this particular structure. So we have this particular structure, sum over the data, which hasn't been seriously looked at by the optimization community. They look at that, but they don't take advantage of this structure. So here, what we do is we take advantage of a structure. Traditional method, they really don't. They have nothing to say about that special structure, while the modern stochastic algorithm to say, you have this structure, you can take advantage of that. And of course, what resulting algorithm is fast rate, but it's sequential algorithm. The real next step is to say, let's say we want to do optimization, parallelization, what we should do. So I give some ideas, but there are really different issues. And I think this is a lot of work can be done to say, you have a sequential algorithm, we know it's good, how we can try to parallelize it. OK, thank you. Basically, for convex problem, we after every 2 iterations, 2 epochs, we update W with the next. Every 2 epochs, we do a W. For non-convex, 5. Let's give you a concrete answer. Non-convex problem, 5 epochs, update W tilde. Convex problem, every 2 epochs.